We hear the word environment all the time, but what is it really? Well, it's not just a bunch of trees and rivers. It's actually a set of invisible rules, a really delicate dance of connections that links the smallest little pond to, believe it or not, our entire planet. Today, we're going to explore those rules and see how they shape literally everything around us.
So let's kick things off with a question. What could a simple fish tank, the kind you might have in your living room, possibly have in common with our vast planet Earth? It sounds like a strange comparison, I know, but the answer? Well, it reveals a fundamental truth about how our world really works.
And here it is. The answer is that they are both ecosystems. See, a fish tank isn't just a box of water with some fish in it. It's a completely self-contained world, a world in miniature. And what's so wild is that the exact same fundamental rules about interaction, survival, balance that apply inside that little glass box, well, they also govern our entire planet.
Okay, so let's take that idea, this world in a jar, and use it to really wrap our heads around what an ecosystem actually is.
Here's the textbook definition, but let's break it down. An ecosystem is all the living things. We're talking plants, animals, even tiny microorganisms interacting with each other and with all the non-living stuff around them. It's this constant dance between life and its physical surroundings. And this breaks it down perfectly. An ecosystem has two halves. On one side, you've got the biotic components, that's all the living stuff, the plants, the animals, you and me. And on the other side, you've got the abiotic or non-living factors, things like temperature, soil, water, and wind. The key thing to remember is that neither side can exist without the other. They're totally intertwined. Okay, so if an ecosystem is like a big stage, who are the actors? In this next part, we're going to meet the cast of characters and the absolutely essential roles they play to keep the whole show running. So it turns out every balanced ecosystem has three crucial jobs that need doing. First up, you've got the producers. Think of plants. They're like the chefs of the world, making their own food using sunlight. Then you have the consumers, like us, who get our energy by, well, consuming other organisms. And finally, you have the unsung heroes, the decomposers. These are the bacteria and fungi, the planet's cleanup crew. They break down all the waste and dead stuff, returning vital nutrients to the soil so the producers can use them all over again. I mean, without them, the whole system would just grind to a halt. All right, so we've met the players, but how did they all connect? Well, it all comes down to energy. And as we're about to see, the way energy flows through an ecosystem follows a very strict and honestly, a kind of surprising rule. We're all familiar with the food chain, right? It's basically a ladder showing who eats whom. Each step on this ladder has a fancy name, a trophic level. It always starts with the producers at the very bottom, then moves up to the herbivores that eat them, and then to the carnivores that eat the herbivores. Seems simple enough, but this is where it gets really interesting. It all kicks off with the sun. Now think about all the massive amounts of solar energy that hit our planet every single day. Of all that energy, the plants, the producers at the base of pretty much everything, can only capture and use about 1% of it. Just 1%. That tiny little sliver of energy is what powers almost all life on Earth. Kind of mind-blowing, right?
And that huge energy drop-off doesn't stop there. This brings us to a super important idea, the 10% rule. When an herbivore eats a plant, it only gets to store about 10% of that plant's energy. And when a carnivore eats that herbivore, same deal, only about 10% of the energy gets transferred. At every single step up the ladder, most of the energy is just gone.
So the obvious question is, where in the world does the other 90% of that energy go? It doesn't just vanish into thin air. It's used by the organism for its own life, for moving around, breathing, keeping warm. It powers that individual's life, but it just doesn't get passed up the chain.
And this is the direct result of that massive energy loss at every step. There just isn't enough fuel left to support really long food chains. After about 3 or 4 levels, the available energy drops off so much that it simply can't sustain another level of predators. This isn't just a random pattern. It's a fundamental law that shapes the very structure of life in any ecosystem on the planet. Okay, so that's how the natural system is supposed to work. But what happens when we humans start introducing things that, well, don't follow the rules? Let's take a look at how our own activities can mess with these finely tuned cycles. One of the most dangerous ways we disrupt things is through a process called biological magnification. This happens with certain man-made chemicals, like some pesticides, that nature can't break down. So instead of getting used up or disappearing, they do the exact opposite of energy. They become more concentrated as they move up the food chain. And here's how it works. A pesticide gets into the soil and is absorbed by plants, but just in tiny amounts. Then an insect comes along and eats lots of those plants, concentrating that chemical. A bird then eats tons of those insects, concentrating it even more. And since we humans are often at the top of many food chains, we can end up with the highest, most dangerous dose of these harmful substances in our own bodies.
Now let's switch gears to another big issue, ozone. This molecule has a really fascinating double life. Down here at ground level, it's actually a pretty nasty pollutant, but way up in the stratosphere, that exact same molecule forms a layer that is absolutely critical for our survival. It acts like a planetary shield, blocking the sun's most harmful UV radiation.
And this shield is made completely naturally. High-energy UV rays from the sun zap and split normal oxygen molecules, that's O2. These newly freed oxygen atoms then quickly find and combine with other O2 molecules to create O3, which is ozone. It's just a beautiful, self-regulating natural process. But then, in the 20th century, we came along and introduced synthetic chemicals called CFCs. You'd find them in things like old refrigerators and aerosol cans. And as these chemicals drifted up into the atmosphere, it turned out they were incredibly good at destroying ozone molecules, which started to dangerously thin out our protective shield. Now, the good news is that this discovery led to amazing global cooperation to ban CFCs, which really shows that we can solve these huge problems when we decide to work together. So, from the global atmosphere, let's bring it all the way back down to the ground. Because the way we handle our garbage is another huge way we impact our environment, connecting these big global problems directly to the choices we make every single day.
The trash we create basically falls into two buckets. You've got your biodegradable waste, like food scraps or paper. This stuff can be broken down by those decomposers we talked about earlier. But then you have non-biodegradable waste, like plastics. And nature just can't break this stuff down. It doesn't get recycled back into the ecosystem. It just sticks around, sometimes for hundreds of years.
And this quote just hits the nail on the head. We invent things for one simple reason, like a disposable cup for hygiene or convenience. But we often don't think about the long-term environmental cost. What seems like a small, totally harmless thing, when you multiply it by millions of people doing it every single day, well, it creates a massive waste problem. So, at the end of the day, it really comes down to this. Every single item we use and then just toss away, whether it's a plastic bottle or a coffee cup, it has a story. It begins its life somewhere, serves us for just a moment, and then it ends up somewhere in our environment. So the only real question left is, what kind of story will the things you use tell?